Hello, everyone, and welcome to my channel. This is an educational channel, and we take a look at great theories of everything and all-encompassing theories and things that you can use to help you with your holistic worldview, your paradigm shifting, your awakening to 5D consciousness. Today is our 506th video that we've done on the reciprocal system of theory from Dewey Bernard Larson. And Mr. Larson was an American engineer who lived in the 20th century, died back in 1990, and he put out a lot of books and articles on his reciprocal system. One of the few scientists who attempted to build his universe out of not matter, not energy, but motion. And in Larson's world, motion is the relationship between space and time. And that is a reciprocal relationship. In Larson's world, motion is a fraction, with space or time as the numerator, time or space as the denominator. Space or time can be in multiple exponents. And so, you can think of speed as the most basic kind of motion. Speed is space over time. The runner is running at 10 miles per hour, 10 miles of space and 1 hour of time. But all of our other scientific quantities are also forms of motion. Matter is a kind of motion. In Larson's system, it's T to the third power over S to the third power. Energy is a kind of motion, T over S. Force is a kind of motion, T over S squared. Acceleration is a kind of motion, S over T squared. Pressure is a kind of motion, time over space to the fourth power. And so on and so forth. And Larson's first fundamental postulate that he came out with in 1959 states that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And then his second of 2 postulates is just kind of the background that he uses to plug in his first postulate. So his second postulate states that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. So he takes his first postulate and plugs it into the second postulate, and eventually arrives, through a process of deduction, arrives at a theoretical universe, what his universe would look like if his postulates were correct. And then he compares his theoretical universe with the so-called actual, measured and empirical universe of the legacy scientists. And he does that in some books that he wrote, including this one that we have in front of us right now called Basic Properties of Matter, where Larson arrives at equations through a process of deduction on many of the basic properties of matter, such as the melting point or the compressibility, and then compares, plugs those in to the elements and many molecules, many compounds, and then compares them with the scientific tables. We're about to start chapter 19 of this book called Magnetostatics. And so this is one of the first chapter that he's done on magnetism after several chapters on electricity. And I must admit that Larson's stuff on electricity and magnetism is my weakest area as far as understanding what he's talking about. And I think some of his followers feel the same way, some of his associates. and that especially with the electricity stuff, he may have made a couple mistakes that ended up costing him. Larson admitted that he was subject to error. He really believed that his postulates were correct, but whether he applied his postulates correctly, whether his chain of deduction was always sound, is a different question, and that he possibly made some errors, and he believed that his errors would be corrected eventually, because the system is a generalized system. It's a theory of everything, and so eventually it would kind of come out in the wash that that there were certain errors in applying the system. And Dr. Bruce Perret has done a lot of work in kind of trying to clean up Larson's electricity and magnetism. But be that as it may, we're going to look at some of those changes eventually, but we want to get it from the horse's mouth here, what Larson has to say about magnetostatics or magnetism or basic properties of matter in general, and then we can kind of take him to task on it. Okay, so starting here, chapter 19. Also, if you'd like to get a more thorough rundown of Larson's postulates, what they mean, how they're applied, just listen to any of my first 474 videos on this subject. At this point, I'm just kind of assuming that you have at least some kind of elementary understanding of Larson before we go into this. Okay, chapter 19, magnetostatics. As we saw in the preceding pages, one of the principal obstacles to the development of a more complete and consistent theory of electrical phenomena has been the exaggerated significance that has been attached to the points of similarity between static and current electricity, an attitude that has fostered the erroneous belief that only one entity, electric charge, is involved in the two types of phenomena. The same kind of a mistake has been made in a more complete and categorical manner in the current view of magnetism. While insisting that electrostatic and current phenomena are simply two aspects of the same thing, contemporary scientific opinion concedes that there is enough difference between the two to justify a separate category of electrostatics for the theoretical aspects of static phenomena. But if magnetostatics, the corresponding branch of magnetism, is mentioned at all in modern physics texts, it is usually brushed off as a, quote, older approach that is now out of date. Strictly static concepts, such as that of magnetic poles, are more often than not introduced somewhat apologetically. This book was written in 1987, so just to give you an understanding of what Larson is talking about when he's referring to the literature that's out there. He's writing back in 1987, or slightly before that. The separation of physical fields of study into more and more subdivisions has been a feature of scientific activity throughout its history. Here in the magnetostatic situation, we have an example of the reverse process, a case in which a major subdivision of physics has succumbed to cannibalism. Magnetostatics has been swallowed by a related but quite different phenomenon, electromagnetism, which will be considered in chapter 21. There are many similarities between the two types of magnetic phenomena, just as there are between the two types of electricity. In fact, the quantities in terms of which the magnetostatic magnitudes are expressed are defined mainly by electromagnetic relations. But this is not by any means sufficient to justify the current belief that only one entity is involved. The subordinate status that conventional physics gives to purely magnetic phenomena is illustrated by the following comment from K.W. Ford. Quote, "As theoretical physicists see it, magnetism in our world is merely an accidental byproduct of electricity. It exists only as a result of the motion of electrically charged particles." The implication of a confident statement of this kind is that the assertions which it makes are reasonably well established. In fact, however, this assertion that magnetism exists only as a result of the motion of electrically charged particles is based entirely on unsubstantiated assumptions. The true situation is more accurately described in the following quotation from a physics textbook. Quote, "It is only within the past 30 years or so that models tying together these two sources of magnetism, magnets and electromagnetism, have been developed. These models are far from perfect, even today, but at least they have convinced most people that there is really only one source of magnetic fields. All magnetic fields come from moving electric charges." End quote. What this text is, in effect, telling us is that the idea does not work out very well in practice, but that it has been accepted by majority vote anyway. A prominent American astronomer, J.N. Bacall, has pointed out that, quote, "We frequently settle important scientific issues by acclamation rather than observation," end quote. The uncritical acceptance of the far from perfect models of magnetism is a good example of this unscientific practice. A strange feature of the existing situation is that after having come to this conclusion that magnetism is merely a byproduct of electricity, one of the ongoing activities of the physicists is a search for the magnetic analog of the mobile electric charge, the electron. Again, quoting K.W. Ford, quote, "An electric particle gives rise to an electric field, and when it moves, it produces a magnetic field as a secondary effect. For symmetry's sake, there should be magnetic particles that give rise to magnetic fields, and in motion produce electric fields in the same way that moving electric particles create magnetic fields." That is the end of that quote. This author admits that, quote, "So far the magnetic monopole has frustrated all its investigators. The experimenters have failed to find any sign of the particle," end quote. Yet this will-o'-the-wisp continues to be pursued with an ardor that invites caustic comments such as this, quote, "It is remarkable how the lack of experimental evidence for the existence of magnetic monopoles does not diminish the zeal with which they are sought." Ford's contention is that, quote, "the apparent non-existence of monopole particles now presents physicists with a paradox that they cannot drop until they have found an explanation," end quote. But he unintentionally supplies the answer to the paradox when he closes his discussion of the monopole situation with this statement, quote, "What concerns the physicist is that, quote, in defiance of symmetry and all the known laws, no magnetic particle so far has been created or found anywhere," end quote. Whenever the observed facts defy the known laws and the current understanding of the application of symmetry relations to any given situation, it can safely be concluded that the current understanding of symmetry and at least some of the known laws are wrong. In the present case, Any critical appraisal will quickly show not only that a number of the premises from which the conclusions as to the existence of magnetic monopoles is derived are pure assumptions without factual support, but also that there is a definite contradiction between two of the key assumptions. As explained by Ford, the magnetic monopole for which the physicists are searching so assiduously is a particle which gives rise to magnetic fields, that is, a magnetic charge. If such a particle existed, it would, of course, exhibit magnetic effects due to the charge. But this is a direct contradiction of the prevailing assumption that magnetism is a byproduct of electricity. The physicists cannot have it both ways. If magnetism is a byproduct of electricity, that is, electric charges in current thought, then there cannot be a magnetic charge, a source of magnetic effects, analogous to the electric charge, a source of electric effects. On the other hand, if a particle with a magnetic charge, a magnetic monopole, does exist, then the physicists' basic assumption of basic theory of magnetism, which attributes all magnetic effects to electric currents, is wrong. It is obvious from the points brought out in the theoretical development in the preceding pages that the item of information which has been missing is an understanding of the physical nature of magnetism. As long as magnetism is assumed to be a byproduct of electricity, and electricity is regarded as a given feature of nature, incapable of explanation, there is nothing to guide theory into the proper channels. But once it is recognized that magnetostatic phenomena are due to magnetic charges, and that such a charge is a type of motion, a rotational vibration, the situation is clarified almost automatically. Magnetic charges do indeed exist, just as there are electric charges, which are one-dimensional rotational vibration acting in opposition to one-dimensional rotations. There are magnetic charges, which are two-dimensional rotational vibrations acting in opposition to two-dimensional rotations. The phenomena due to charges of this nature are the subject matter of magnetostatics. Electromagnetism is a different phenomena that is also two-dimensional, but involves motion of a continuous rather than vibratory nature. Now again, that is how the reciprocal system works. Everything in the reciprocal system is a kind of motion. And in Larson's system, a charge is a kind of motion. It is a rotational vibration, kind of like this. And, you know, in two dimensions, that would be a little bit harder to express, but Dr. Bruce Perret tries to do that, and we'll get into that at a future time. But in Larson's system, the electron is an uncharged particle, which is a rotating unit of space, a kind of motion, a rotating unit of space. Just like everything else in Larson's system is a kind of motion. And so in magnetism, magnetic charge is a two-dimensional rotational vibration that can be applied to a two-dimensional rotation. The two-dimensionality is the key to understanding the magnetic relations, and the failure to recognize this basic feature of magnetism is one of the primary causes of the confusion that currently exists in many areas of magnetic theory. The two dimensions of the magnetic charge and electromagnetism are, of course, scalar dimensions. The motion components in the second dimension are not capable of direct representation in the conventional spatial reference system, but they have indirect effects that are observable, particularly on the effective magnitudes. Let me get into that just a second. So when Larson is talking about building a universe of motion, he is particularly talking about what he calls scalar motion. Scalar motion is a motion that has a magnitude, but it has no specific direction. You can envision scalar motion with a balloon that you put dots on. Put dots on the balloon, and then you blow up the balloon. All the dots will be moving away from each other, but in no specific direction. Every dot will be moving away from every other dot. So every dot will be moving in every direction outward. And if you contract the balloon, then every dot will be moving toward every other dot, and not in any specific direction. Now, this kind of scalar motion, the outward motion Larson calls the progression, the inward motion Larson calls gravitation. And in Larson's system, there are 3 dimensions. That's part of his first postulate. You know, the universe is composed entirely of motion, existing in 3 dimensions. That is 3 dimensions of space, 3 dimensions of time, and 3 dimensions of motion. But it only requires 1 dimension of motion to describe 3 dimensions of space and or 3 dimensions of time. So the second and third dimensions of motion cannot be described by a stationary spatial reference system. Okay, so when he's talking about a second dimension of magnetism in this case, he's not talking about a second dimension of space. That's not what we're talking about. I have some friends who I've exposed to the reciprocal system, and they dismissed Larson basically because he says that magnetism is 2-dimensional, and that goes against what they understand. But it's not a second dimension of space. It is a second dimension of motion, which goes beyond not only a second dimension of space, but beyond a third dimension of space. You need 3 dimensions of space just to describe 1 dimension of motion. And this is moving into a second dimension of motion, what he calls scalar dimensions. That's why Larson has what he calls the natural reference system. This is a moving reference system, and it goes beyond what a spatial or temporal reference system is capable of expressing. So we have to be kind of in this space of imagining a phenomena that cannot be described by your typical stationary spatial reference system. Okay, back to the text. Larson, lack of recognition of the vibrational nature of electrostatic and magnetostatic motions, which distinguishes them sharply from the continuous motions involved in current electricity and electromagnetism, also contributes significantly to the confusion. Magnetostatics resembles electromagnetism in those respects in which the number of effective dimensions is the determining factor, whereas it resembles electrostatics in those respects in which the determining factor is the vibrational character of the motion. Our findings show that the absence of magnetic monopoles is not a defiance of symmetry. The symmetry exists, but a better understanding of the nature of electricity and magnetism is required before it can be recognized. There is symmetry in the electric and magnetic relations, and in some respects, it is the kind of symmetry envisioned by Ford and his colleagues. One type of magnetic field is produced in the same manner as an electric field, just as Ford suggests in his explanation of the reasoning underlying the magnetic monopole hypothesis. But it is not an electric particle that produces an electric field. It is a certain kind of motion, a rotational vibration, and a magnetic field is produced by a similar rotational vibration. The electric current, a translational motion of a particle, the uncharged electron, in a conductor produces a magnetic field. As we will see in chapter 21, a translational motion of a magnetic field likewise produces an electric current in a conductor. Here, too, symmetry exists, but not the kind of symmetry that would call for a magnetic monopole. The magnetic force equation, the expression for the force between two magnetic charges, is identical with the Coulomb equation, except for the factor T over S introduced by the second scalar dimension of motion in the magnetic charge. The conventional form of the equation is F equals m prime over d squared, the distance, the two masses over the distance squared. As in the other primary force equations, the term m prime and d squared are dimensionless. That I'm not really getting, but we'll move on. From the general principles applying to these force equations as defined in chapter 14, the missing term in the magnetic equation, analogous to 1 over S in the Coulomb equation, is 1 over T. The space-time dimensions of the magnetic equation are therefore F equals T squared over S squared times 1 over T equals T over S squared. Now, I smell a rat there on that derivation of the units for Larson's magnetic equation here, but we will get into that at a later time. Like the motion that constitutes the electric charge, and for the same reasons, the motion that constitutes the magnetic charge has the outward scalar direction. But since magnetic rotation is necessarily positive, time displacement, that is, the atom is made out of two-dimensional rotations. In the material sector, the sector that we reside in. But since magnetic rotation is necessarily positive in the material sector, all stable magnetic charges in that sector have displacement in space, and there is no independent magnetic phenomenon corresponding to the negative electric charge. In this case, there is no established usage that prevents applying the designations that are consistent with the rotational terminology, and we will therefore refer to the magnetic charge as negative rather than using the positive asterisk designation as in application to the electric charge. Although positive magnetic charges do not exist in the material environment except under the influence of external forces in a situation that will be discussed later, the two-dimensional character of the magnetic charge introduces an orientation effect not present in the electric phenomena. All one-dimensional electric charges are alike. They have no distinguishing characteristic whereby they can be subdivided into different types of classes. But a two-dimensional magnetic charge consists of a rotational vibration in the dimension of the reference system and another in a second scalar dimension independent of the first, and therefore perpendicular to it in a geometrical representation. The rotation with which this second rotational vibration is associated divides the atom into two halves that can be separately identified. On one side of this dividing line, the rotation appears clockwise to observation. The scalar direction of the magnetic charge on this side is therefore outward from a clockwise rotation. A similar charge on the opposite side is a motion outward from a counterclockwise rotation. The unit of magnetic charge applies to only one of the two rotating systems of the atom. Each atom therefore acquires two charges, which occupy the positions described in the preceding paragraph and are oppositely directed. Each atom of a magnetic or magnetized substance thus has two poles, or centers of magnetic effect. These are analogous to the magnetic poles of the Earth and are named accordingly as a north pole or north-seeking pole and a south pole. These poles constitute scalar reference points, as defined in Chapter 12. The effective direction of the rotational vibration that constitutes the charge located at the north pole is outward from the north reference point, while the effective direction of the charge centered at the south pole is outward from the south reference point. The interaction of the two magnetically charged atoms therefore follows the same pattern as the interaction of electric charges, as illustrated in Figure 22, which is identical with Figure 20 of Chapter 13, except that it substitutes poles for charges. Chapter 13 was on the static electricity, and so it substitutes poles for charges. Two north poles move outward from north reference points and therefore outward from each other. Two south poles similarly move outward from each other. But as shown in line B, the north pole moving outward from a north reference point is moving toward a south pole that is moving outward from a south reference point. We will get into that tomorrow a little bit deeper. We'll start reading this chapter, reading this same paragraph over again tomorrow when we resume. But that is all for today. Thank you for tuning in, and have a